This is lesson 2.1, inductive reasoning and conjecture. For number 1, write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. So a conjecture is a concluding statement reached using inductive reasoning. And inductive reasoning is reasoning that uses a number of specific examples to arrive at a conclusion. So when you assume that an observed pattern will continue, you are applying inductive reasoning. So it's the process of going through a number of specific cases and seeing what happens and observing a pattern, and when you observe a pattern, making a statement about the pattern that you see. So in number 1 we have $4.50, $6.75, $9. So in our solution here, $6.75 is $4.50 plus $2.25. $9 is $6.75 plus $2.25. So each cost is $2.25 more than the previous cost. So with that said, this is our conjecture. Each cost is $2.25 more than the previous cost. And use your conjecture to find the next item in the sequence. So the next item in the sequence would be $11.25. For number 3, we have this pattern, and we can see that the shaded part is going clockwise to the next position. So the next position would be right here, as we can see in this figure. So this part is shaded, and our conjecture would be in each figure the shading moves to the next point clockwise, and then the next figure would look like this. For number 5, we have 3, 3, 6, 9, 15, and if we add the first two terms, we get 6. If we add the next two terms, we get 9. 6 and 9 gives us 15. So our conjecture would be each element in the pattern is the sum of the previous two elements. And the next term, we would have to add these two numbers together. So we would get 24. For number 7, make a conjecture about each value or geometric relationship. And so we want to make a conjecture about the product of two even numbers. So the process here to make a conjecture is we have to look at specific examples. So product, multiplication, two even numbers. So let's take 2 times 2, we get 4. Take 2 more even numbers, 2 times 6, we get 12. Test another pair, 2 times 8, we get 16. And you don't have to do 2, you could do anything. 10 times 10. Okay, we get 100. So the thing that we want to observe are these numbers and what is always true about them. And that would be our conjecture. So the product of two even numbers will be an even number. And number 9, the relationship between the set of points in a plane equidistant from point A. So equidistant means the same distance away from point A. So if point A is here, I go this distance in this direction, the same distance in that direction, same distance, and I just continue this. So I'm getting these points, and all of these points form a circle. So get rid of that. So the set of points in a plane equidistant from point A is a circle. This is our conjecture. Okay, for number 13, we want to find a counterexample to show that the conjecture is false. So a counterexample is a specific case that proves excuse me, that our conjecture is false. So to show that a conjecture is true for all cases, you must prove it. It takes only one false example to show that the conjecture is not true. The false example is called a counterexample. It can be a number, a drawing, a statement. It's one specific case, and that's all we need, which disproves our conjecture. So it says here, if a ray intersects a segment at its midpoint, then the ray is perpendicular to the segment. So, you could have a segment like this, and, the midpoint and a ray intersecting it, and it is perpendicular. Then you can have another segment. Here's another case, and at the midpoint, it's intersecting, and once again, it ends up being perpendicular. So, you can have a million different segments where this is true, where it is perpendicular to the segment. But then, let's say on the 1,000,001st time, the next time that you draw a ray intersecting a segment at its midpoint, and the ray goes in this direction, and obviously it's not perpendicular, this is not 90 degrees, this would be our counterexample. This proves that this statement is false. If a ray intersects a segment at its midpoint, then the ray does not have to be perpendicular to the segment. It can form a different type of angle. So once again, this drawing, this diagram, is our counterexample to this conjecture. For number 15, write a conjecture that describes the pattern in each sequence. Use your conjecture to find the next item in the sequence. So we have 3, 6, 9, 12, 15. These are multiples of 3. So if we take 3 plus 3, we get 6. 3 plus 6, we get 9. 3 plus 9, we get 12. 3 plus 12, we get 15. So our conjecture would be each element in the pattern is 3 more than the previous element. And then the next part of our answer, we want to find the next item in the sequence. So the next item would be 18, 3 plus 15. For number 17, we have 2, 22, 222, 2,222. So we can see pretty easily here that each element has an additional 2 as part of the number. So this is our conjecture. Based off of this conjecture, then the next number, well, just add another 2 to it. So we have 22,222. On number 19, we have 1, 1/2, 1/4, 1/8. So in our work here, we see that we're taking each element and multiplying it by 1/2 to get the next element. So taking 1/2 times 1/2, and we get a 4th. Taking a 4th times 1/2, and we get an 1/8. So our conjecture, each element is 1/2 the previous element, or the previous element times 1/2. So now we need to take 1/8 times 1/2, and we get the next element, 1/16. Percent humidity, 100%, 93%, 86%. So each time we're subtracting 7%. So our conjecture, each percentage is 7% less than the previous percentage. And our next element, subtract 7% from this element, and we get 79%. Number 23, for our club meetings, we have January, March, May. So we can see that we skip a month, or that each meeting is 2 months after the previous meeting. So go 2 months later from May. So the next item in the sequence would be July. For number 25, we observe the pattern here. We can see that we're rotating in this direction. So our conjecture, in each figure, the shading moves to the next area of the figure counterclockwise. And here's the next item in the sequence. Okay, for 27, we look at our pattern here. We can see that this triangle is moving clockwise. So we know what the next figure will look like. And our conjecture is the shading of the lower right triangle and the upper right quadrant of the first figure moves clockwise through each set of triangles from one figure to the next. In number 29, when there is a shortage of water, some municipalities limit the amount of water each household is allowed to consume. Most cities that experience water restrictions are in the western and southern parts of the United States. Make a conjecture about why water restrictions occur in these areas. So, dry, hot conditions can be caused by a lack of rainfall. When there is little to no rainfall, water stores cannot be refilled. There is increased demand for water for lawns and gardens. It is drier in the west and hotter in the south than other parts of the country, so less water would be readily available. For 31, we want to make a conjecture about each value or geometric relationship. So we want to conjecture about the product of two odd numbers. So once again, we want to test specific cases. So we want to multiply two odd numbers together. 3 times 3 equals 9. 101 times 3 equals 303. 99 times 9 equals 891. And we observe the product that we get here. So in each of these cases, we get an odd number. So then we can say that the product of two odd numbers is an odd number. For number 33, the relationship between A and C, if AB equals BC and B is not equal to 0. So we want to test specific cases here. So let B equal 3. So in order for these two to be equal, A and B would both have to be 2. Whoops, I'm sorry. If B is equal to 3, A and C would both have to be equal to 2. In the next case, if B is equal to 5, A and C would both have to be 100. In the next case, if B is 59, then we'd have to have 9,999 for A and C. So the only way for this to be true is that A and C would have to be equal. The relationship between segment AB and the set of points equidistant from A and B. Once again, equidistant means the same distance from. So the points equidistant from A and B form the perpendicular bisector of segment AB. A perpendicular bisector is a line, a ray, or a segment that splits another segment in half and is perpendicular to it, or it intersects at the midpoint and forms a right angle. So basically what we have here is the segment AB. That's what we're starting with, and then we're finding distances from A and B that are the same, okay, the same distance, and we get a point, and we continue this process. So this distance and this distance are the same, and we get a point here, and we continue this on and on and on again, okay, and these two distances are the same, and we get a point, and we continue that, continue it, continue it. So we have this collection of points, and that's all a line is a collection of points. So we have all these points here, and we observe that it bisects the segment because it's equidistant from the two endpoints, and it makes a right angle. So it's perpendicular to that original segment AB. Number 37, the relationship between the areas of a square with side x and a rectangle with sides x and 2x. So to get the area of a square, we square a side. So the area of the square would be x times x, or x squared. To get the area of a rectangle, we multiply length times width. So the area of the rectangle would be 2 times x squared, or 2x squared. So we observe this area and this area. So we have x squared for the square, we have 2x squared for the rectangle. So our conjecture would be the area of the rectangle is 2 times the area of the square. We can even test this with numbers. So let's say that the side of the square is 3. Okay, so we would take 3 squared for the area of the square, and that would be 9. And then the rectangle would have sides of 3 and 2 times 3, or 6. So 3 times 6 would give us 18. So if we look at 9 and 18, 18 is 2 times the area of the square, which is exactly what our conjecture is. For number 41, determine whether each conjecture is true or false. Give a counterexample for any false conjecture. So number 41, if x is an integer, then the opposite of x is positive. So our integers are the numbers on the number line, including 0. So we have negatives, positives, and 0. And this is saying you can take any integer, take the opposite of it, and you'll get a positive. Well, this is a false statement, because any time you take a positive number, so our answer would be false. For example, suppose x equals 2. This is saying when you take the opposite of 2, you're going to get a positive. Not the case here. If you take the opposite of 2, you get negative 2, which is a negative. So 2 is a counterexample. It proves that this is a false conjecture. There are many counterexamples to this. So consider the case of 3. Okay? So if I take the opposite of 3, do I get a positive? No. I get a negative. So 3 is another counterexample. Number 43, if you have 3 points, A, B, and C, then A, B, and C are non-collinear. So this is saying, take any 3 points, and they will not lie on the same line. Well, we know that this is false. Our counterexample would just be a diagram showing that you could have 3 points that are collinear. So this diagram is our counterexample, proving that this is a false statement. Number 45, if the area of a rectangle is 20 square meters, then the length is 10 meters and the width is 2 meters. So this is saying we know the area is 20, then we will assume that the length will always be 10, the width is 2. And we know that this is a false statement. So our counterexample, we need to come up with a case where our area is still 20, but our length and width are something other than 10 and 2. So it is false. Counterexample is right here. The length could be 4 and the width could be 5, because if we multiply those two numbers together, length times width, we still get 20, proving that this is a false statement. For number 47, numbers that can be represented by evenly spaced points arranged to form a geometric shape are called figural numbers. For each figural pattern below, part A, write the first 4 numbers that are represented. So let's do part A first. We notice in our pattern here, we would just have 1, count up the points, we have 4, and then 9 here, and 16. Part B, write a conjecture that describes the pattern in the sequence. So our answer here is that we can start by adding 3 to 1 to get the second number, 4, continue adding the next odd number to the previous number to get the next number in the sequence. So we're adding 3 to get 4, the next odd number would be adding 5 to get 9, the next odd number would be adding 7 to get 16, and so on. Part C, we want to explain how this numerical pattern is shown in the sequence of figures. So, each figure is the previous figure with an additional row and column of points added, which is 2 times the position number minus 1. And when I say position number, I mean the next column and the next row. So this would be position number 1, position or column number 2, column number 3, so position 3. 1 is subtracted since 2 times the position number counts the corner point twice. So if we were to add 2 times 3, or 6, that would be 1 too many points, because we can see that we have 1, 2, 3, 4, 5 points. And then in the next diagram, we would take 2 times 4, which is 8, which is 1 too many, because we have 1, 2, 3, 4, 5, 6, 7. So we have to take 2 times the position number minus 1, which is always an odd number. Part D, find the next 2 numbers and draw the next 2 figures. So if we add the next odd number, we would be adding, let's see, we added 7, so then we want to add 11. Sorry, add 9 points, and then add 11 points. So in this diagram we can see this would be position number 5, so we're taking 2 times 5 minus 1, so we're adding 9. And then this would be position number 6, so 2 times 6 minus 1, so 12 minus 1, we're adding 11 points. So we would get this figure and then this figure by adding 11 points. In number 51, we have gold box conjecture. Gold box conjecture states that every even number greater than 2 can be written as the sum of 2 prime numbers. For example, 4 is an even number greater than 2, which can be written as the sum of 2 prime numbers, 2 and 2. 6, once again, an even number greater than 2, and then we have the sum of 2 prime numbers, 3 plus 3. 8, an even number greater than 2, and then the sum of 2 prime numbers, 3 and 5. So part A, show that the conjecture is true for the even numbers from 10 to 20. And that's what we have here. So 10 can be written as 5 plus 5, 12 as 5 plus 7, 14 as 7 plus 7, 16 as 5 plus 11, 18 as 7 plus 11, and 20 as 7 plus 13, where we're taking the sum of 2 prime numbers, numbers that are only divisible by themselves, and 1. Part B, given the conjecture, all odd numbers greater than 2 can be written as the sum of 2 primes. Is the conjecture true or false? Give a counterexample if the conjecture is false. So there are many cases where this is true. For example, if we take 5, we can express 5 as the sum of 2 primes, 2 and 3, or 7. Okay, so 7 is a non-odd number greater than 2, which can be written as the sum of 2 and 5, or 9 can be written as the sum of 2 and 7. So there are many cases where this is a true statement, but can we find one case, that's all we need, a counterexample, which will make this a false statement? It doesn't matter if it's true 100 times. If we can find one case, then this is a false statement. And here's our counterexample. So 3 cannot be written as the sum of 2 primes. 3 we would have to write as 2 plus 1. 2 is a prime number, 1 is not.